think the thing that impresses me about my field is that we have surprisingly little understanding of the fundamental ways in which electrons behave. So if you go to really complicated materials, we normally think about things like superconductors. It turns out that there are fairly simple equations you can write down for how a superconductor behaves. And a superconductor is best described as behaving in terms of electrons that are well localized. So even though you have a solid state material, that's what superconductors are, you also have a mixture of electron localization and delocalization. Delocalized electrons are spread out all across the material, and they behave like they would in a metal. And so that interplay between localization and delocalization, if you can describe it correctly, you can describe how sometimes materials are metals and sometimes materials are insulators. And you can also describe superconductivity. So some of the most complicated materials phenomena we know are well described as long as you know you have to treat those two things on an equal balance. It turns out that when you want to solve the difficult equations on a computer to do electronic structure theory correctly, in order to predict a catalytic material or predict properties that you might care about for any application, what we tend to get wrong is we tend to get the localization and delocalization wrong. It turns out it's incredibly hard to get both of those right. And so either we over-localize the electrons or we over-delocalize the electrons. And so my group's really focused on right now understanding how and why we get those things wrong, how wrong we are for different types of materials, or how right we can be. And our interest is in really fundamentally improving both the accuracy and understanding when a prediction made on a computer is likely to be wrong. And specifically for molecular and supported molecular catalysts, because those have single site transition metals where that interplay of localization and delocalization governs chemical reactivity. So examples of this would be hemoglobin, so the way in which we take on oxygen and breathe even is governed by a transition metal. And in order to understand how that works, how it can bind oxygen and release oxygen, or how we can even breathing in certain gases like carbon monoxide are dangerous because they bind too strongly to that, those are all governed by how well the electrons localize or delocalize. And so while we've made great strides in computational modeling, things like the Materials Genome Project, all of those are hindered right now by the ability to predictively model what transition metals are doing. If you look at the most exciting materials for any kind of chemical conversion, they always have transition metals at the heart of them. And chances are when modeling is getting done, it's done incorrectly right now because we still don't, as a field, know how to properly localize or delocalize electrons.